All right, so we're going to move on to Laszlo Keszthelyi, who's going to give the next talk. Laszlo, you can bring your slides up. And data products needed to identify lunar ice reserves.
So I'll talk about data products needed to identify lunar ice reserves. And co-authors are here to USGS. You can go ahead and skip over the outline slide too. So yeah, you can skip that one too. Because it would jump straight into definitions to talk about what am I talking about when I say ice reserves. Okay, so resources are, in the lunar context, are something on the moon that you can convert into a commodity. A commodity is something that you can use. On Earth, is typically something you'd pay for. A deposit is a concentration of that resource, and if it's a widely distributed deposit like lunar regolith, you can call it a continuous deposit. And reserve is a resource that can be converted into a commodity within your budgets. Here on Earth, we have a well-developed economic system where you can convert pretty much everything into a dollar value. But for the moon, for space missions, we're in a more earlier stage than that. So it's important to look at the different budgets you have: cost, mass, power, volume, etc. Perhaps most important is risk. How much risk are you willing to accept? So what you call a reserve depends on how much risk you're willing to accept and the capabilities of your mission. So for this discussion, you can go jump to the next slide. We'll baseline the concept that was published in Kleinhans and Paz for 2020, where the goal was to go into the permanently PSRs, the permanently shadowed regions inside craters, and process about 15 tons of ice per year out of the regolith, digging roughly a meter down and working with regolith that had a few percent ice. And while there's plenty of other concepts out there, I think this is typical enough for our ideas to get an idea of what kind of measurements we need to be able to say we have a reserve. We found ice that we can work with. And so 15 tons per year for this kind of concentration means working in an area that's a few tens of meters in diameter per year. We excavate and process the ice out of it. So if that's what you're looking for, then the scale of the mapping needs to be at that roughly 10-meter scale. But looking at lots of different craters. And the ice concentration estimates need to be good to about 1%. You need to be able to confidently estimate how much ice is there to roughly that level. And for this kind of discussion, I think that's good enough. So next slide. And then the USGS has a methodology for doing mineral resources. They have a somewhat different one for doing energy and doing water. And we've tried to combine these to look at how we might do a lunar resource assessment. And the key part here is just you break up the problem into smaller pieces and you calculate statistics in each of them and then combine them at the end to come up with what you predict the chances are of finding what you need to work with in different locations. So we'll take a look at the kind of data products you need to be able to successfully complete each piece of this process. So next slide. So for the formation model, that's a basic understanding of how the ice got there, which is necessary to understand where you expect to find ice and where you don't expect to find ice. The product that you're going to find that in is peer-reviewed scientific publications. That's the thing that says, okay, we have products you can point to and say, we know how the ice got there. The spatial model, which is saying where the conditions are favorable for ice, we're already generating these models based on our current best guesses for how the ice got there. And so we have multi-kilometer scale ice favorability maps, which combine topography, orbital elements, thermal physical properties, age of the surface, and so forth into models to generate estimates of which parts of the moon are favorable and not so favorable. And these can get refined, but we know what those look like. What we don't have are data products that tell us about the density, the quality, and the quantity of deposits of ice on the moon. And in order to get that, you need to combine, well, especially on the scale that we want to identify reserves, you need to have in situ data at that 10-meter scale you're not going to get without in situ data. But in order to understand both poles, you're going to have to combine that with orbital data. You're not going to get 10 meter per pixel data across the entire poles in situ. So there's a fine art in combining in situ ground data with orbital data. And those are the products you really want. So the next slide. And then what we call an economic model that combines concept of what is technically recoverable. So we have an engineering ability to get at the ice, but there's also what are we going to be allowed to do legally? And at some point, if you start digging up enough of the moon, people are going to start complaining. So, and I think at the scale we're talking about here, few tens of meter diameter spots in permanently shadowed craters where nobody can see it, there's going to be a lot less pushback on it. It's something to keep in mind. But to do this, you need maps of things like rover scale maps of trafficability. Where can you get power? Where can you get communication? Which areas are keep out zones, perhaps for making sure that you're not impacting things that the Artemis astronauts are trying to do. And then you take all of this data and you combine it statistically using Monte Carlo methods. And since you're doing this in a computer, it's essential that all the data is in a format that computers can understand. So different types of raster files, shape files, algorithms, so forth. So all the products need to be stuff that the computer can understand. And then perhaps the really key point is if you want to come out with a measurement of your risk, the probabilities of finding the ice you need to have well quantified uncertainties. So that's not just the data values. These products, like things like trafficability, there's a lot that goes into models of taking the raw data coming from the instruments and turning it into an interpretation. And then you need to know the spatial accuracy of the data as well, especially if you're starting to do correlations and your two data sets are not lined up correctly. You're going to get garbage out because the data are not lined up with each other and the correlations won't mean anything. So last slide, I'm just going to hit the key points again. In order to get to the point that we're talking about reserves and not just trying to assess broadly what resources exist in the moon, we need to combine the ground truth data and orbital data. That's the only way you're going to get the spatial resolution and the extent that you need. Then the other key point is that going toward reserves, you're talking about data products that involve a lot of interpretation. They're highly derived data products. So things like ice favorability maps or trafficability maps, these are not simply the output from some instrument. So you need to understand not just the uncertainties within the individual measurements, but you need to understand what goes into the model, the assumptions that are in them, the uncertainties and all the different inputs before you have an understanding of the uncertainties you have in these highly derived data products. And that takes a lot of work. And it's hard to find data products where that level of investigation to uncertainties has been published, especially in a format that's easy for people to understand. And you can, of course, skip all that and not worry about the uncertainties. But then you're in a position where you have to accept unquantified risk. You don't know what the chances are that you have the ice you need. You just have a gut feeling. This looks good. And I don't think most people want to invest a space mission in that kind of situation. So I love the idea of an international effort to do all this. And we do need standards. Those standards need to include a understanding of how to quantify and explain the uncertainties in the data products. Thank you.